morning, good afternoon, good evening, or good night for joining this session on performance evaluation optimization. So our topic is performance evaluation and modeling of the full verification system and its components. So the session is convened by Mr. Li Peng, who is the Deputy Secretary General of China Arms Control and Disarmament Association, and myself, Thierry Héritier from PTS, together with Joseph Villa, who will deal with the question answers. So we have 5 presentations in this session. And in order not to waste time, I will give the floor to the first presenter that will talk about signal injection as a means to exercise the entire CTBT monitoring regime. Stephen, the floor is yours.
Thank you. First of all, can you hear me?
Can you explain? We can hear him. We also have his presentation in video.
Yeah, but it's the video.
Okay, can you hear me?
No. But
if you hear me, Stephen, we are going to play the video and then you'll have the question answers after, if it's okay for you.
Yeah, I'm sorry if you can't hear me.
No, we hear you loud and
Oh,
clear.
you hear me? Okay, but you're not seeing it. All right, let me try one more time. Sorry.
No, we see you.
You hear and see me. All right. Thank you. Well, I'm sorry about that. Not sure why it's not displaying correctly here. Okay, so you see my presentation and you see and you see all right. There we go. Hi, my name is Stephen Creek, and thank you for that brief introduction. I'd like to talk to you a little bit about a technology I highlighted at a prior S&T meeting called the Radiation Field Training Simulator, which was a technology that injected signals and used location-based scenarios to control operating radiation detection systems, which are used broadly by emergency responders. They're also used in our IMS sensor networks, the radionuclide stations, and they're used in on-site inspection equipment. The approach of signal injection enables far more sophisticated analysis, or excuse me, exercises to be conducted because we're not limited by the kinds of radiation sources that one can deploy. We're only limited by our imagination. And so I'd like to talk to you a little bit today about how signal injection might be used to enhance the ability to conduct exercises using the entire system that we have spent so many decades putting together. The goal, of course, is to exercise our people and our equipment and all of the processes as a whole system against the most realistic scenarios as possible. This increases the confidence in what we're doing. It can also show the community that we ultimately get the right answer. But can we actually exercise the whole system? And what I mean by that is everything. Can we actually synthetically generate an event, transmit everything through the earth and the environment to radionuclide and other IMS stations, and ultimately have the analysis done by IDC and NDCs? And if OSI equipment were to be fielded and make measurements at that location of this event, would we actually get the answer that we expected and we started with? And when I'm talking about exercising, I'm also not just really talking about injecting data into the system, which is what's done routinely. I'm actually talking about much more than that, which is including exercising physical hardware itself to include all of the data management and handling and transmission, as well as everything downstream of that, because I think that actually would be much more representative of what a real exercise would be. So before I talk about this in detail, let me talk a minute about what we currently do. We currently exercise components of this system. We exercise through exercises, IMS data analysis. We have the ATM challenge was something talked about yesterday. We send radionuclide samples around the community to exercise the laboratories, and occasionally world events give us an opportunity to test the whole system in some component anyway. But those are often unplanned, they're episodic, and they don't generally exercise everything. We supplement that by conducting field exercises. Many of you know we've spent an enormous amount of effort doing field exercises like IFE 14, but those are very expensive and they can only occur very infrequently as a result of that. And even for as good as they are, they're very good at testing things like logistics. We still can't replicate the nuclear explosion phenomena and scales that one would encounter in a real event situation. So over the last few years, you've perhaps seen some discussion about synthetic event generation in other parts of our community. I'm a radionuclide person, but there are some discussions of using synthetic event generation in the seismic community. And so what I want to talk to you now is a bit about how we can take that sort of approach much further. But for just a moment before I do that, let me talk to you a little bit about how we already track our performance. We track our performance through a variety of means. We know, for instance, when systems are up and down in the field, and in many cases, like radionuclide cases in particular, the background can actually tell us whether or not those systems are operating as we expect them to. And we have occasional failures that lead to investigations and mitigations to resolve those failures. We spend time examining those, and we also spend time conducting workshops and occasionally going out into the field and calibrating these instruments. But what we don't do when one considers all of that earlier exercising that I discussed, as well as this performance modeling, what we still don't do is we don't actually exercise everything as an integrated system, where what we start with are signatures that are consistent with a nuclear test explosion, and where we actually think we know the answer that we could judge ourselves against at the end. So based on some work I've done with emergency responders, I wanted to explore the use of signal injection as a way to exercise our whole system. So I want you to consider the following. The models right now are getting really pretty good, and one could consider an idea in which we use those source term models to calculate for a particular location at a particular time what the seismic signals would look like, what the radionuclide source term would look like, and that we could then use our other models like ATM models and Earth propagation and other models to transit those signatures through the air and through the through the Earth. Until they arrive at IMS stations at a particular location, where we can calculate what those signatures would look like at each of those IMS stations by using sensor response functions, since we know how these sensors work really well. And as I said earlier, if we were to display, or if we were to deploy on-site inspection equipment to that event location, we'd like all of these sensors that are in that field location. And in many cases are very similar to the kinds of sensors that are at the fixed IMS locations, to get signatures that are consistent with what that source term was that we started out with in the first place. I mean, wouldn't it really be great if we could do exercises like that? Now, I want to say this is possible now for a couple of reasons. First of all, for all the differences that we scientists like to argue about how much better radionuclide is versus seismic, or the other way around, all these sensors act as a transducer. They all do much the same thing. They take a signal from one form and they convert it into another. In the case of radionuclide sensors, they're converting it into spectra that we use and do analysis on. In the case of seismic sensors, they're doing that with ground motion, and hydroacoustic sensors are doing that with underwater pressure changes, and of course infrasound are doing it with sound. But they all wind up with digitized pulses at the end that are collected into some form, either a time history or an energy binning of some sort, and then transmitted to the IMS or the IDC for analysis. What I want to suggest now is that we can actually synthesize all of that and make detector systems do that through processes similar to what was demonstrated with this radiation field training simulator for active radiation detection systems. The technologies are emerging, as many of you know, that are shrinking the space between what's real and what's virtual. Virtual reality technologies are really now becoming commonplace. And a number of years ago, I brought a technology to Vienna to demonstrate how you can show harmonization between different radiation detection systems if you conduct them under the same scenario. This is an example of a dosimeter and a gamma ray spectrometer on the back of someone walking into a radionuclide debris field. Can show how computers can actually show how these things would operate in a harmonious way. And then I mentioned this technology earlier, but at 2 S&T meetings ago, I demonstrated how signal injection can be used to control the operation of radiation detection systems. I can feed into them realistic data that is analogous to the kinds of source terms one might expect in an on-site inspection. And that all of these things together could be used as a means to inject signals throughout the entirety of our system to really replicate both the signatures that we want, as well as in the case of this RAFS device, someone carrying it around in the back, they get to experience all the physics. If they approach a source, they get to observe that. If they collect a spectrum, they get to analyze that data, maintaining all the realistic physics that they would have in that particular source encounter. And I want to mention that while this is somewhat notional now, the RAFS technology has been commercialized, and it will begin appearing on the market soon, and because other communities are demanding technologies such as this. They cannot replicate, nor do they want to bear the cost of fielding really high activity or hazardous radiation sources, nor do they want to expose themselves unnecessarily to radiation dose. So we're going to find in the next few years that these technologies that enable signal injection into operating systems are going to appear on the market, and that they will make it possible for us to consider exercising in this way. Now, with all that being said, there are pros and cons to thinking about exercises in this way. On the pro side, it's a very powerful message, in my opinion, if one can exercise a system end to end and get the answer that you expect. I think it's also something that we talk about in the joint expert group, a way to demonstrate through routine exercises, data fusion that we talk about in the J group all the time. This is a way you can actually realistically demonstrate it. And controlling stations, if we were to actually enable signal injection through stations, could enable other things. It could enable a routine and remote maintenance, like pushing software updates. It could also enable performance monitoring of physical hardware itself to try to catch a failure before it occurs. On the con side, though, this is something that we cannot currently do. It is very potentially complicated to execute, requiring exquisite timing in some cases. We don't currently have the infrastructure for transmitting information in reverse and for doing remote maintenance, for example, but that isn't impossible. And OSI instrumentation is not really part of the system at the moment, so that would have to be something integrated. But back on the pro side, you could envision a model, though, where we could conduct exercises and also study performance of systems in a different way, where we could monitor change times, collection times, and show how that works. But if we were to do that, or if we were to interfere with the operation of the systems themselves, one might worry about whether or not we would still have confidence in them, and what happens if our models are not good enough and we don't get the right answer. But as I said, a lot of this is coming in reality, and we're going to find that some of these commercial systems appear on the market where we could take advantage of them through routine upgrades. But we haven't really considered this yet, and so that's really the purpose of my talk today, because I want to talk about things about equipment specifications. And so while it's still early, I want to bring this approach to your attention, because I think the earlier the better. We could envision doing exercises in a more realistic way, and I've described very briefly how one might be able to do that. And because the technology is closer than we think, it may be upon us before we expect it. And since it is early, we can actually consider different implementation options, how one might actually do it. And that starting those technical considerations earlier might enable us to factor them into such things as equipment specifications. So that's all I have. Just wanted to bring that to your attention, and thank you very much.
Thank you very much, Stephen, for a very interesting and promising presentation for the years to come. I'm afraid we are a little bit short of time, so I suggest if you have questions, you would directly address Steve and his team to get the answers to your questions. So we move to the next presentation, which will be the National Data Center Preparedness Exercise, Scenario Design and Expert Technical Analysis, that will be presented by Ole Ross.
Thank you, Terry, and giving me the opportunity to present the National Data Preparedness Exercise 2019. Many of you know the series of National Data Center Preparedness Exercises. It has now a 14-year-long history of scenario-based, potentially treaty violations or potentially treaty-relevant cases. We had many non-compliance scenarios, we had compliance scenarios, and they increased in complexity. Of course, the goal of such exercises is to give the NDCs the opportunity to practice and to test routines and to exchange among each other. But the exchange is something which came a bit short with the NPE 2019 because COVID-19 dropped into the disclosure process. So the 2019 NPE was designed by a common endeavor with Italy. So from the Italian radionuclide NDC, the colleagues invented the story of the scenario and the radionuclide sources. And the German NDC assisted with atmospheric transport modeling, with the organizational framework, and with the waveform part. The starting situation of the exercise was just that a fictitious state around the Alps announced a reactor incident. So, say that at a research reactor, they had a small release of radionuclides, but nothing dangerous. And after that, there were some simulated concentrations occurring in the IMS. So a widespread occurrence of particulate radionuclides, but also noble gases at the Schauenstein station. But the situation was quite puzzling still for the participants. And the idea in this exercise was to evolve it from step to step, so that we realize various entry levels for different levels of skills or technologies which are applied in the NDCs by adding information from time to time. And so, as this was still quite puzzling, looking for the backward ATM and the potential source regions of events, then the fictitious neighbor state, Istria, joined in, who had some national measurements of radio xenon in its city, Vienna. And as you know, there is the mean of expert technical analysis in the treaty or in the protocol to the treaty, so that a member state can ask for technical assistance and providing relevant data to the IDC. And as there was the series of expert meetings dealing with that since October 2018, the idea was to include this tool into the NPE 2019. So this fictitious state attempted to request expert technical analysis from the IDC. And as Istria isn't existing, actually, then the German mission on behalf of Istria requested such expert technical analysis. Of course, we notified beforehand the IDC director that we planned such a thing, and so that they were prepared. And so Istria provided those additional national xenon measurements and then asked for backward atmospheric transport modeling to confine further a potential source region of relevant waveform events. Also asked for additional search for waveform events in the potential source region, and asked for radionuclide analysis. Although it was shortly before Christmas, the IDC reacted fast, so the after this first ETA request ever, the first exercise straits requested methods report, how the product is called, which is generated by ETA request, was given. And the results of the stage requested method reports stick to the questions of the request. So the ATM has shown potential source regions. They searched for waveform events only in the IDCA products in the pipeline, and so they found also one event here, a small earthquake on morning on the 30th of July with magnitude 2.9, which was actually the right place, but the event which we thought of as a scenario was 5 or 6 hours earlier, was a 3.7 local magnitude earthquake in the Bodensee, in English Lake Constance, quite shallow earthquake, which was the scenario event which we thought of. And in the last step of the exercise then, we distributed to the participants synthetically manipulated waveform data. So we changed the seismograms of this earthquake, or we provided 2 days of mini-seed data, but within this data, one event was changed so that it got a more explosion-like character. So as you see here on the right, the waveform-oriented experts at NDC could have detected this now in the data. And so it's finally quite clear what it was like as a scenario. It was a non-compliance scenario, but the particulates originated from the spent fuel of the research reactor. So it was an intentional release of Raziel to distract from the other release. And the other release was the noble gas release from the Bodensee. So the scenario was a nuclear explosion in the ground of the Lake Constance. It was also quite special that due to the forward ATM at Schauensland, we had at RM33, we had a mixture with real background concentrations, which at that time did not come from fluorescence, which is quite special. So we didn't know that beforehand, but it turned out in the analysis afterwards. And unfortunately, in the distribution of the concentrations, there were some flaws in the particulate scenario, which made it more difficult and more puzzling even to solve this scenario, as the barium lanthan was meant to be in equilibrium because the fuel was some months outside, and there was also a switch in the cesium ratios. So overall, it was quite a tricky scenario with many aspects, but unfortunately, due to COVID and other circumstances, until now the results of the NDCs are not discussed at a venue like the NDC workshop. So we will have a short slot on Friday afternoon in the NDC session where we will discuss the way forward and how to proceed with the NDC process, NPE process. And after then finished this NPE 2019, there's still place on the world map for much more NPE scenarios. Thank you.
Thank you very much, Ole, for your presentation. We do not have any question at this point in time, so perhaps I suggest we move to the next presentation and we'll see if question comes during the minutes that follows. So the next presentation will be the seismic network geometry optimization using a fully automated stochastic method. And we'll have the the record of the presentation of Said.
Good afternoon, everyone. This talk is about introducing a new approach for designing a seismic network based on an easy-to-use but very powerful method called the fuzzy self-tuning particle swap optimization for evaluating the performance of an active seismic network, or even for designing a new one based on improving earthquake location parameters like hypocentral error reduction. The items I will talk about shortly starts with a summary of the study region, then a very light introduction of Iran National Seismic Broadband Network, afterwards a very short discussion about the proposed method, and finally we have the results. Our study region is Iran, which is really famous for seismology society because of the high rate of seismicity that we have here. Very large earthquakes have occurred throughout the history in this region, and Iran and also surrounding area in general are prone to severe destructive earthquakes. Unfortunately, most of them caused many people died or heavy damages imposed to infrastructures and buildings. So having a reliable catalog of earthquakes and identifying the seismic sources and fault geometries could provide very helpful information for scientists, engineers, and decision makers to try to reduce the risk of large earthquakes and really do disaster mitigation and management. So it's very clear, if we want to reach that goal, we need as much as possible the sufficient and accurate amount of data to being analyzed for producing strategic models. One of these tools would be having an efficient seismic network. Currently, there are two national seismic networks operated in Iran, which one of them is Iranian National Broadband Network. We call it BIN afterwards. That you can see its station distribution here. It's started since 2004 with only 4 active stations, and now it reaches 35 seismic stations, mostly equipped with corrupt sensor and digitizers, working perfectly in a broad range of frequency. Since the IRSC seismic network, the other network in Iran, which is belonging to Tehran University, is responsible for detecting and alarming earthquakes, this network was designed basically for research and education in all aspects related to seismology, earthquakes, engineering, and disaster risk management, and suggesting practical approaches as well as supporting their implementation in order to reduce the risk of earthquakes and to develop the safety culture against earthquakes in Iran and the region. As we definitely know, an optimized seismic network could be evaluated based on its performance and the accuracy of event locations recorded by the network. So we use this criterion to redesign the network geometry in order to improve its performance. So firstly, we selected 13,000 events with magnitude larger than 3 recorded by BIN network since 2004. Then we relocate them using hyperellipse location program and a minimum 1D velocity model to get the initial status of the performance of the network. Next, we assumed these events as the reference points and calculate synthetic true-base events. We used PyConnell, a Python package for generating accurate synthetic travel times for each event station pairs. In the last step, we used the FSTPSO methodology to find the best possible station coordinates in order to get the significant improvement in the event location accuracy based on hypo-7-bound criterion by means of horizontal and depth error, RMS, and azimuthal gap. To get more reliable solution also, we repeat the procedure for 10 times each run, including 100 random models, and finally take the mean of new station coordinates as the final output. Here we can see the initial status of the BIN network based on the calculated horizontal error for earthquakes in the selected areas dataset. According to the current geometry of the BIN network, for the most of events located in the central region, the horizontal error is less than 5 km, which is quite good. But for the most events distributed in the western and southwestern part of the region, it exceeds more than 10 km, which is not really good, reminding that the western part is the most active one. Applying the proposed method for finding the best possible station coordinates suggests that the total shift of about 7 and 6 degrees in latitude and longitude respectively are required. According to the shift vectors between the initial and the proposed location of the seismic stations, it reveals that the most required shifts are often needed to be considered in those stations located in the western part and those which are placed near the boundary. Relocating all events with optimized seismic network increases the event's location accuracy at least for 15%, especially for the events distributed in the western part. The mean value of the horizontal error is less than 6 km now, which is showing a 40% improvement compared to the initial status of the BIN network. Based on hypo-7 quality control parameters, 35% of total events in the selected dataset lies in three classes A, B, and C, according to this table, using the BIN seismic network, and this value could level up to 48% using an optimized version of the network. So at the end, we believe that the proposed method is capable of designing a new seismic network or redesign an old one to increase its performance. The new design network is structured based on the recorded events by or after network, so the increases in event location accuracy of the network can be achieved more easily. Finally, we also suggest using this method as a performance evaluator for any permanent or even temporary seismic network. Thank you very much for your attention.
Thank you very much, Said, for this very interesting presentation. We do not have question at this point in time, so I suggest we move to the next presentation. And in case we have a little time at the end, we may come back to some question that came at a later stage. So next presentation will be Bayesian localization of infrasound events with propagation meta model. And we have the recording of Christophe Millet's presentation.
In this presentation, I'm going to talk about Bayesian localization of infrasound events with propagation meta models. That's a common work with Julien Vergoz, Alexandre Goupy, and Didier Lecan. A model-based study needs a source model, atmospheric specifications, and a propagation model. You have essentially two categories of propagation models. The physics-based models allow computing sensitivities that can be used to characterize the source. We can use for that variance-based sensitivity analysis, which decomposes the variance of each output into fractions, the so-called Sobol indices. For example, for signals recorded at the Norwegian station IS-37, we obtain that 80% of the variance associated with the duration is caused by the variance in the first input, which is attributed to atmospheric fluctuations. 5% by the variance in the second, the source model, and 10% due to interactions between the two. However, estimating such sensitivity indices is computationally demanding. On the other hand, empirical and stochastic models can be run on a desktop computer, but these models do not include the current state of the atmosphere. There are some important challenges in infrasound propagation modeling. Incorporating full-wave propagation models in the IDC network processing, quantifying the various sources of uncertainties. How can we do that in this presentation? I'll propose a method that combines a Bayesian framework and meta-modeling. Now we will consider the model as a black box between X and Y, except for the classification tasks. The output Y takes continuous values as X is varied. When asking for the probability of an event, a natural choice is to use the Bayesian approach, which provides a rule for updating an initial hypothesis, the prior, using the so-called likelihood. As a function of Y, with X fixed, it indicates the compatibility of the evidence in red with the given hypothesis, X. P of D doesn't matter, it's just a normalization constant. Within the Bayesian framework, the question then arises as to how you can compute the posterior. An answer can be given if you have a model that provides reliable estimates of various statistics of Y. A model is an abstraction of phenomena in the real world. A meta-model is yet another abstraction, highlighting properties of the model itself. In this study, we use polynomial chaos expansions, which can be viewed as an interpretable machine learning regression algorithm to predict quantities of interest Y given the location and time of the infrasound event X. Once the coefficients have been computed, the output Y and statistics can easily be computed. Let me now give you a numerical recipe that combines the Bayesian approach and meta-models. This is called the GPC algorithm. You need as input the prior, which is provided here by IDC. Then you generate a random sample using this prior. You compute signals for each of the sample. You extract the quantities of interest from signals, and then you compute the coefficients. So thanks to Norbert for that. Norbert Wiener was an American mathematician at the MIT. In 1948, he had published Cybernetics, a landmark theoretical work who influenced the arrival of computing, robotics, and automation. Okay, the third step is to extract the quantities of interest. And for that, you have essentially two approaches: from the similarity between two signals via extracting a vector of quantities of interest, arrival time, and so on. But extracting the quantities of interest and arrival time from noisy signals introduce uncertainties. And these uncertainties can be quantified using random variables. In the present study, for the arrival time, we define it as the time for which the amplitude of the RMS first exceeds a given threshold, beta times the maximum amplitude of the signal. Of course, you have to do that for each recorded signal in red and for each computed signal, yellow here. For the sake of simplicity, we will restrict our analysis to 6 infrasound stations. For a given source position, here provided by IDC and an atmospheric specification, signals can be computed with increasing complexity. Source at ground level and 1-dimensional atmospheric specification, source at 25 kilometers altitude, and range-dependent acoustic propagation. The simulation data are produced by a normal mode-based model, which belongs to the class of the full wave models. But how do we explain such differences in the numerically obtained waveforms? For a fixed source position, the variability of the medium along the source receiver path can be quantified using the effective sound speed ratio. However, since the wind profile depends on latitude and longitude, a change in the position, X, can affect acoustic ducting at source location in terms of the maximum ratio RZ over a range of altitudes. The prior for X, once decided, produces a PDF, a probability density function for RZ, with either efficient wave propagation when you consider profiles at the source, or unfavorable propagation conditions when instead you consider the average profiles along the source receiver path. The practical implication is that small uncertainties in the source location may result in large changes in statistical properties of wave propagation. Finally, while physics of propagation is well captured by the meta model, polynomial chaos expansion can also be used to derive various statistics of Y, such as its moments and its sensitivities to different components of X with no extra numerical cost. You simply need to sum up over the proper set of indices. Now we'll consider the Bering Sea event. This event is known to correspond to a small asteroid that exploded at roughly 25 kilometers altitude over the Bering Sea. According to NASA, the event, the second largest of its kind observed in the past 20 years, released an estimated 173 kilotons of energy. Propagation conditions can be quantified by RZ as a function of latitude and longitude using the source location of the IDC, which is here given by the grand star. The solid black line for which RZ equals to 1 splits the domain into regions where sound waves propagate efficiently and regions where the stratospheric waveguide weakens or disappears. For eastward and southeastward propagations, the waveguides weaken along the path and may literally disappear. For northeastward propagation, IS-53 and IS-18, the ducting layer is formed at altitudes above 40 kilometers at source location and gradually spreads downward as the range increases. So uncertainty on the position directly translates into range-dependent atmospheric uncertainties via the atmospheric specifications. For each of the plausible locations, a complete simulation is done for computing the arrival times as functions of X and beta. From this sample, we have computed the coefficients of the polynomial chaos expansion at each station. These meta models are very cheap from a computational point of view and can be used to generate the surface response on a thinner grid to get a precise localization. This figure gives the marginal distributions for the location and the time of the event for given hyperparameters of the PDF for beta. Confidence regions can either be computed or approximated using a normal distribution. Another choice for the hyperparameters provides another confidence region. Normal mode methods can also be used as a range-dependent tool using the adiabatic approximation, which assumes that in going from one range to the next, the modes couple without any transfer of energy to the other modes. So back to the inverse problem, we observe that using the same parameters for beta provides a maximum a posteriori probability, which is closer to the NASA estimate. Adding range-dependent effect is therefore essential. We can assess the impact of each station in the localization process. The figure gives the number of stations for which the partial likelihood is significant. This indicates that around the maximum a posteriori, the likelihood takes information from mainly 4 different stations, which guarantees a robust localization. Other maps for different values of beta give similar results. On the right, you get the station with maximum likelihood. From these maps, you can compute even metric and decision analysis. You can also compute likelihood ratios and many other colorful representations. The purpose of this presentation was to show that meta model purely trained on a few simulated data, less than 100 cases, yields reliable probability distributions of location and time of real-world infrasound events. And second, the Bayesian inference problem can be reformulated to incorporate both simulated data and uncertainties associated with extracting the quantities of interest. Of course, there is a need to identify the precise role of each uncertainty source, the model uncertainty, quantities of interest, using the sensitivity indices. Other approaches lead to similar trends, but uncertainties have not the same meaning. Now we plan to apply the Bayesian approach to the web. Finally, I'd like to emphasize that under fixed computing budget, no more mod expansions can be truncated using model reduction algorithms. So thank you for watching, and now it's time for questions.
Thank you very much, Christophe, for a very dense presentation. Actually, we have one question that relates to the uncertainty in the picking methods, and how do you quantify that, and does it have practical implication on your Bayesian method?
Okay, thank you, Thierry. That's a very interesting question and one of the purposes of this study. In fact, although full wave modeling is better suited for propagating low frequency waves, it's true that there is the question of how the uncertainty associated with an automated picking method affects the localization accuracy. In this study, we have used a moving root RMS of a sliding window and criteria based on random threshold through beta. Now, if we turn back to the results, clearly, even large uncertainties on picking do not affect significantly the maximum a posteriori probability for the location estimate, except obviously if the standard deviation of the threshold beta is too large. And indeed, much of the emphasis in this work was to show that range-dependent propagation effects dominate over the peaking uncertainty.
Okay, thank you very much for, I guess, a clear answer. We don't have any further question at this point, so I suggest we go to the last presentation and see if we have a little time for question that may come in the time. So our last presentation will be Metrology for Low Frequency Sound and Vibration, an introduction to the Infra-AUV project. And we have the video for that.
Hello and welcome to the presentation Metrology for Low Frequency Sound and Vibration, an introduction to the Infra-AUV project. My name is Thomas Bruns. I'm scientist at the PTB, the National Metrology Institute of Germany, and the coordinator of this European funded project, which was starting last autumn and is running for 3 years altogether, and which I would like to bring you a little bit closer now. The mission of this project is to deliver the link between the International System of Units and the International Monitoring System for acoustic and seismic measurements. The link to the International System of Units is an aspect that we consider very important for all kinds of measurements that have a certain responsibility or importance for the public. And it's still missing for the International Monitoring System. This link is usually provided or realized by a chain of calibration that starts at national metrology institutes and national standard calibration facilities and is going down a sequence of calibrations until it reaches the target, like a seismometer for an international monitoring or an IMS station, monitoring station. This chain of calibrations is also, to some extent, the basis of the structure of our project, which is organized in work packages. And the first 3 you see here in this chain are calibration work packages. Work package 1, primary calibration, then we have a secondary calibration, work package 2, and an on-site calibration work package 3. So you already see here that it all boils down to calibration of IMS station sensors. We also have a work package 4, which deals with consequences or benefits from our work, and a work package 5, which is responsible for the impact of our project. So basically the publication and distribution of the results. Now I would like to go through the work packages to explain you a little bit closer what we have in mind. The work package 1, primary calibration. Primary calibration means to realize a calibration based on the units according to standardized methods. It's usually a quite complex process in the laboratory, like, for example, for vibration, using laser interferometers to measure the movement of sensors or measurement equipment. It's performed in well-controlled environment in the lab and with a lot of effort, but we gain the lowest measurement uncertainties from this because we are very close to the basis of the units. It's generally well established in the metrology institutes for the fields we are discussing here, but not so much for the low frequencies that are required by the CTBTO and by the IMS measurement station. So in this project, we focus on extending the frequency range. And in some areas, we also have to deal with new methods to extend the frequency range. If we have a primary calibrated sensor, so the start of the calibration chain, we can go to the secondary calibration, which is typically a simpler process, but still in the laboratory. So we calibrate a sensor by comparing it to another sensor. For example, the primary calibrated reference. So we can calibrate a microbarometer with a reference microphone, for example. The measurement uncertainty in this secondary calibration, of course, inherits from the primary calibration. So you cannot get better than your primary calibrated reference by secondary calibration. But another aspect of secondary calibration is that you can use it for sensors which are not accessible by primary calibration methods. In acoustics, for example, MEMS sensors, which are available in large number on the market nowadays, they are not accessible by primary calibration methods of today. So here again, we have to extend the frequency range to lower frequencies, and we have to find appropriate reference sensors to use for secondary calibration in the low frequency range. Once we have the calibrated sensors, we have the strong intention, of course, to go on site in the field and calibrate a station or a station sensor by a transfer standard primary calibrated in the laboratory. Here we face some challenges that, at least to the metrologists in our collaboration, are quite unusual, which like limited accessibility or limited maintenance of the stations. Also, the uncontrolled environment is kind of a real challenge with high or low temperatures, and then we have to deal with uncontrolled arbitrary signal sources. We cannot generate a pure sine for a seismic station, for example, or for an infrasound station in the ocean, a hydroacoustic station in the ocean, sorry. So here we have first to evaluate suitable signal sources for the calibration. Then we have to take care of the impact of environmental conditions that is not very well known to us. And we have to develop procedures to get to a transfer function information for our sensors based on arbitrary signals, for example. Along the way, we have to deal with measurement uncertainties, and this is the first and maybe the most important aspect of the work package 4, the measurement uncertainty propagation from the primary calibration to the operation on site. The other thing is that we hopefully have learned on the route how to do it right, so we know good practice and we want to compile it in a good practice guide to make it available to others. We have been asked during the planning of the project what will be the impact, and one of the impact we think that will be generated is on modeling. We know that IMS data is currently also used for environmental monitoring in terms of weather conditions or climate change, and we would like to showcase how known uncertainties, measurement uncertainties, impact on such models. In addition, for you, maybe more a side effect. For the legal metrology, it's one of the most important aspects. We will support things like noise assessments in the infrasound area. Imagine wind parks or wind energy plants close to human dwellings. There's a large discussion in many countries about the infrasound impact on the population without the availability of reliable measurements. So there will be some development in that area as well. So we evaluate uncertainty of measurement, we draft the best practice guide in Work Package 4, and we showcase the impact on environmental monitoring. This all will be distributed in Work Package 5 impact based on 4 pillars, the usual publications in scientific journals, but also contributions to international standards like to IEC or ISO documentary standards, presentations at scientific conferences, training workshops that we plan to have together with CTBTO. And of course, we are on a website and are active in some social media. So in the end, what will be gained from Infra-AUV? It's international acceptance of the measurement results because they are traceable to national measurement standards, to the SI, and there is an international treaty of mutual acceptance of such measurement results with such calibrations. You will have improved direct quantitative comparability of the sensors and the stations as a whole, and the option for traceable sensor replacement, because with a traceably calibrated sensor, you have an absolute scale backing your measurement results. You will have a reliable knowledge of measurement uncertainty, which will help you to use the data later on with known certainty or uncertainty. And we will provide good practices for the use of the uncertainty in modeling, for example. We, that are the institutes, where you find the logos down here on this almost last slide, and the co-authors that are listed here. Of course, there are many more participants in this project, not all named here. And here you find our website and our Twitter. So thank you for your attendance, and I'm open for questions.
Well, thank you very much, Thomas, for this presentation. This is probably a very important topic for CTBTO, and it's not always the most popular one and we have seen many presentations during the week where people are more and more demanding accuracy and the modeling or the processing with the data is becoming more and more advanced, and this issue of characterizing as well as possible the sensor is becoming more and more central. So thank you very much for presenting this initiative. We have the question to you. So I read the question. I wonder how the environmental parameter could be a priori specified. Have you any plan of experiment-based approach for that?
I'm sorry, I did not get the first part of the question.
It's about how the environmental parameter could be a priori specified, and have you any plan of experiments-based approach for that?
Yes, actually, for example, at PTB, we have a facility where we, for example, can calibrate accelerometers, or in this case, seismometers, using a climate chamber. So for this case, for example, we have actually facilities at the National Metrology Institutes or the primary laboratories to simulate some of the environmental impacting factors, at least. For others, we may rely on on, let's say, weather data together with historic data in the databases from national data centers or from the CTBTO to evaluate the impact on drift, for example, or something like that.
I thank you very much for your answer, and this is a very good transition with a question that came up for Stephen at an early stage. And the question was related to the problem that you mentioned during your presentation, Stephen, is, so I read the question: why to practice on a system that is working all the time? Couldn't a detailed continual performance of the system balance this approach?
Yes, thank you. Thank you very much for the question. So yes, you're correct that the systems are operating all the time, but in many cases they're not exposed to the signatures that are consistent with a nuclear test explosion. So the operators that receive data from them, or the operators that are actually using the instruments in the field, in the case of an OSI, are only getting part. They're only experiencing part of what they would really experience. And so the idea is to complement what we currently do by adding the realism of the signatures that are expected, and to do that in a way that actually tests the operators of those instruments in addition to the instruments themselves. So in the case of OSI, for example, it's important how the operator is carrying the instrument. Do they take it to the right source location? Do they turn it on and collect data in the way that you want them to? And we don't get those kinds of aspects with the ways that we do training currently, unless we do things like bring synthetic sources to the field, which is just hard. So I think this adds to it. There is some concern, however, as I tried to say in my presentation, that you don't want to interfere with how systems are currently operating, right? So one would need to think about how that could be done in a way that doesn't interfere with the continuous monitoring function of IMS stations, for example. But I think it adds to it.
Yeah, thank you very much. It's a very good point. I suspect the question that was asked was rather relating to the international monitoring system than the on-site inspection, actually. And in the case of the IMS, of course, you have on one hand an advanced performance monitoring system, on the other hand the rare events, which are precisely the one for which you would like to do the simulation. So thank you very much for the answer.
Thank you.
There is another question to you that was, it's a question of Xavier Blanchard that relates to the OSI, but I think you could give an answer that could be probably broadened to beyond the on-site inspection only, and that was, could the simulators also be used for remote online training? And for example, trainees going through scenario from their computer or things like that.
Yes, thank you. So the way the concept was developed is that it's tied to the actual instrument. So as whoever is operating the instrument controls what feedback they get. The only thing that the RAFS device does is use its location and a predetermined scenario to give the operator the feedback. So if an operator is controlling the instrument remotely, there's no reason they can't turn it on and collect data and pull data back to themselves remotely. That would be true both for a fixed sensor in a given location, like an IMS station, or if it were a sensor in motion, like one might expect in an on-site inspection.
Thank you very much for the answer. I think so somehow that there is a yes around your answer under very well-controlled conditions. So I think we don't have a question at this point. No. I would like to thank you very much for the really excellent presentation we have this afternoon, and that are very much forward-looking to what's going to happen in the years to come. So again, thank you very much. And if we don't have any further question, I think we will end the session. Thanks again, and good night for those that are very late in the day.
Bye.
Thank you. Bye.
Thank you.